Hello, dear students. Today I'm planning to discuss with you about accuracy and precision of measurements. And as for simplicity, I was thinking about showing you this simple example. This is a screw, and I have a ruler here for measuring the physical size of this screw. And now I'm measuring this one to have the length of 60.3 millimeter. But then imagine that you were asked as an engineer to sit down by a conveyor belt where these screws were produced. And you're not measuring only one produced item, you're measuring maybe 100 or 1000 of these screws. Then I think you can imagine that you're expecting a certain variation of the values that you actually are concluding that, yeah, in next case maybe it will be 60.0, and then in another case it will be 60.1 and 60.4, 60.3 and so on. You will have a certain variation of the measured values. And how then will you be able to describe the value in the most accurate way? Can you really select just one value and say that, yeah, this screw is 60.1 millimeter, or do you need to somehow also handle the specification of the variations of the length? And also, how can you handle the specification of the possible error of this? I mean, this measuring device that you're using here, how accurate is this one? So these are the kind of questions I would like to raise now in this video presentation. Let's continue and have a look on the next slide. You can imagine that this is a target at the shooting range, and there will be a competition between two shooters, and the two shooters also have two different guns, and both shooters are able to fire off like 8 bullets. And then the first shooter will produce this kind of picture from his 8 bullets, and those bullets are very well they are hitting in a very narrow area, but still quite far away from the position where he was aiming. So I would say that the precision of this shooter was very high, but then the accuracy was lower because he is far away from the center where he was aiming. And the second shooter, his bullets are more spread and for a larger area. So the precision is worse, but then the accuracy is better because those bullets are closer to the center where he was actually aiming. So I'm giving you this example to give you kind of a better feeling for what is meant by precision and accuracy. Yeah, I think you can already now understand that what I'm planning to talk with you about in this video is really much related to and boils down to the subject of statistics, which is applied mathematics. This was a very simple example, but I think we need to have an example that is closer to our area of interest. And hey, by the way, who's told you that statistics is boring? I think statistics is really interesting, especially and fun, especially when we can apply it on our area of interest within embedded electronics, computing and metrology. So let's move on to an example that is maybe closer to our area. What you see here is a voltage meter, and this is a battery. And then you can imagine that we are producing these batteries at a factory, and then we are taking a large population of measurement values that we define as xk, where k is the number of samples in this large population. Yeah, we measure the voltage of a sample of much larger population of batteries, which means that we are taking out we are measuring a small sample of this larger population. And we are going to use this small sample for the analysis of mean value and variation on the battery voltage. But then comes the question how to accurately specify the voltage if there are variations, and for sure we can expect to have variations. and how to specify the uncertainty of that sample data, and what impact has the instrument's calibration error on the measured values. I should say here also that for all of these samples in this large population, then we are using only one single instrument for measuring these values. And if there are any kind of calibration error, then we can expect this error to show as a systematic error in the statistics. So we are bringing out, and we are taking one sample out of this larger population, and here is the n-sized sample that we refer as to SI, where I is the index of the measured sample within this, the measured value within this sample. And how can we now specify the uncertainty of this sample of data? That is the questions. Well, we can start with computing the histogram of the frequency of occurrence of the values, and we can see here that we have a certain variation, of course, of the measured values as we are expecting. On this axis you see the values of the sample data, and here is the frequency of occurrence of those values. Yeah, we can assume now that the variations we see among this large set of batteries is Gaussian distributed. It looks pretty much like a Gaussian distribution, and it is uncorrelated, like white noise model. Yeah, for variations that we see in most real world applications, we see a Gaussian distribution, and very often also there is like uncorrelated variations. So this white Gaussian noise is a quite reasonable assumption in my opinion, and for sure it also makes the computations more easy. So let's now continue with making the mathematical developments. We can say that ST is the true mean value of the sample, and the sample was this limited amount of measured values that we take out of a larger population. The true mean value, yeah. But then the measured mean value is the one that we can compute from n number of measured values, and is an estimation of the expected value mu s. And S0 to Sn minus 1 is then single samples of S being a series of n measured values. Delta S is the systematic error, in this case caused by calibration error of the voltage meter. This we discussed in the beginning. And systematic errors are most commonly referred to as accuracy, and are errors that can be predicted. So this is a deviation from the true mean value and from the value that we can actually measure, the mean value, which is an estimation of the expected value, and this is the accuracy error, delta S. Obviously now we cannot just say that the true mean value is the same as the measured mean value. We rather want to say that the true mean value is the measured mean value minus the accuracy error delta S, plus minus u, where u then is an interval that can be used to specify the variation that we have among the measured values in the sample. Or simply we can maybe say also that the true mean value is the measured mean value plus minus the interval, if we can neglect the systematic error that are stemming from the instrument. But still, the question remains, how can we select a confidence interval u, and at what confidence level certainty? Which means that if we are using an interval of u, at what certainty can we say that the measured voltage is within this range? So let us assume that we have this a situation where we can neglect the accuracy error and the true mean value st is equal to the measured mean value plus minus the interval u. And then we specify the normal distribution according to this formula, where sigma is a measure of the variation and mu is a measure of this center of gravity, where we have the position of the distribution. Then the probability p that the measured value S mean is within the range of S mean plus minus u. We can compute this as an integration of all the probabilities of the distribution from the range of minus u to plus u. This is denoted by this formula, the integration from minus u to plus u. And this integration formula can maybe easiest be computed in computers using simulation methods, numerical simulations. And in this example, I've been generating a graph in MATLAB for sigma equal to 1 and then for mu equal to 0. And then we have it for different size of the intervals ranging from 0 to plus minus 4.5. And then we, for instance, we can make a note that for sigma equal to 1, which is exactly 1 standard deviation, then the probability is 0.68. So for plus minus sigma, then we have 68% of confidence that the measured value is within the specified range. So the conclusion that we can draw from this diagram is that the larger we select u, then the larger the confidence interval will be, and the larger confidence interval that we have, then the larger the confidence level will also be. This can be rephrased as if we select a larger u, a larger confidence interval, then the confidence level will also increase, because we have a less accurate specification of the voltage. But if we want to have a narrow, very exact specification of the voltage level, then also the confidence level, the certainty, will decrease. This kind of makes sense, I think. And I have summarized this into this graph that you see here for plus minus sigma, 2 sigma and 3 sigma. And for plus minus 1 sigma we have 68% of confidence level, plus minus 2 95.4, and plus minus 3 99.7%. And the conclusion that you can also draw from this is that if you really want to reach like 100% of confidence level, then you must also increase the confidence interval, this u, to plus minus infinity, which is maybe not like really realistic. The parameters for the distribution mu is estimated by the mean value calculation for n samples, and the parameter for the variation of this distribution is estimated by the standard deviation computed according to this formula. So I think we now are ready to specify the battery voltage for a sample of produced batteries. This sample that of n measured values that we take out of a large, infinite large population of measurement values. And the voltage of the battery is the mean value of the sample minus the accuracy error, this calibration error of the instrument. We assume that the accuracy error is equal to the calibration error of the instrument, plus minus the standard deviation of the sample at a confidence level of 68%. So we were able to specify the battery voltage based on the calibration error of the instrument, which is a systematic error, and the mean value and the variation that we can measure on a small sample from a larger population of measured values. But the question still remains on when we measure the mean value of this small sample of a larger population, how large do we really need to make this sample in order to have a reasonable good estimation of the mean value of the whole population? So this is the kind of question that I would like to raise now, and it really boils down to our second experiment, which you see here. The same kind of equipment, this voltage meter, and we are going to measure the batteries, and we have a large population of measurement values, and we take a smaller sample out of this n-size sample. So now we would like to estimate the mean voltage for a large population of batteries produced at the factory, not only specifying the mean voltage of this small sample, or rather kind of estimate how good does the mean value of this sample represent the mean value of the whole population. Measurements are done at factory in real time, and for that reason large samples can be problematic for speed. So it's kind of a trade-off from speed versus the estimation accuracy of the mean value for the large population. We see a variation of this sample that correspond to a Gaussian distribution, and we assume that we are dealing with white noise here. It is realistic, and it also simplifies the computation, as you will see. So let us assume now that we compute the mean value of an n-size sample at all possible locations within a larger population of measured data. This is the larger population of measured data, and then for the n-size sample that we position at all possible locations here, we compute a new stochastic variable S mean that is computed from n number of samples within n number of measured values within this sample. And after the computation of the mean value at all those positions, the deviation of this mean value will be the deviation of the whole population divided by the root square of n, where n is the size of the sample. And then we can estimate the variation of the population by the standard deviation of the sample S, and divide this by the root square of n. So the larger the sample size n that we select, then the closer to the population mean the sample mean S mean will become, due to the fact that the variation for this S mean variable, which is a stochastic variable that we see here, that variation will decrease as we also increase the size of the sample. So we are now ready to specify the mean battery voltage for the whole population. So the mean voltage for the batteries of the whole population is equal to the mean value for the sample minus this calibration error, which is a systematic error, plus minus the standard deviation of the sample divided by the root square of n, where n is the size of the sample, at the 68% of confidence level, because we are using plus minus the standard deviation. So this is our conclusion from this experiment. Yeah, I'm now going to try to summarize what was said in this video presentation about statistics, and yeah, we have access to a large population of measurement values, and from this large population we take a small sample of measured values. And from this small sample of measured values, we were able to specify the battery voltage, and we took into consideration the calibration error of the instrument being a systematic error, an accuracy error. And the variation of the measured values within this sample we specified at a given confidence interval, assuming a certain confidence level, a certainty. And then secondly, we were studying the computation of the mean value from this smaller sample of the larger population. So the question was like, how close to the mean value of the large population is the mean value that we compute on this small sample? And we could conclude that the larger we select this small sample, the closer to the mean value of the large population will become, and we will be able to specify the mean value of the large population more accurately the larger we take this n-size sample. So that was about statistics applied on measurement values and metrology, which I think is quite fun and it's interesting. I hope you agree with me and that you are willing to spend some time to try to understand this and maybe read some other literature about statistics. Good luck to you all.